This video is brought to you by Morning Brew, a free daily newsletter that delivers the latest business news from Wall Street to Silicon Valley directly to your inbox. Succinct and witty, it makes reading the news a fun way to start the day. Use the link in the description below and sign up for free now.
Hey, it's Professor Dave. Let's talk about carboxylic acids and derivatives.
He knows a lot about the science stuff. Professor Dave explains.
So we've looked at a lot of chemistry involving carboxylic acids, but now let's do a little bit of a comprehensive survey of carboxylic acids and their derivatives. So obviously you want to remember what a carboxylic acid is. That is this here. So that's abbreviated COOH, or a COO group. And so we know that we have a carbonyl next to an OH. That is a carboxylic acid. And as we replace OH with other groups, we can start to get what we call derivatives of carboxylic acids. So if we take away the OH and we place a chlorine atom, that's going to be called an acid chloride. So that has some interesting utility. Then we can have something called an acid anhydride. This is pretty interesting. We've got a carbonyl, an oxygen, and then another carbonyl, and we have alkyl on both sides. R prime merely indicates that these need not be identical alkyl groups. They could be identical, they could be different alkyl groups. So that's an acid anhydride. And then, of course, we can get an ester, which is carbonyl and then OR. So it's different from a carboxylic acid because instead of a proton, we've got more alkyl on the other side of that oxygen. So this is no longer an acid. There's no acidic proton there. Then, in addition, we can have amides. And so, sorry, this is not amine, this is amide. So we can have an amide where we have a carbonyl and then nitrogen. So instead of an oxygen there, we've got carbonyl, nitrogen. And this can be a primary, secondary, or tertiary amide. If we have NH2, so we just have two hydrogens, that's going to be primary. If one of those hydrogens is replaced with some alkyl group, that's going to be a secondary. And then if we've got no hydrogens, but instead two more alkyl, which can be the same or different, right? We've got R prime, R double prime, then that can be a tertiary amide. So those are some of the derivatives we're going to be talking about. Carboxylic acids themselves are very common. There's a lot of naturally occurring carboxylic acids. So, for example, acetic acid is what gives vinegar its sour taste. Carboxylic acids with short chains are found in dairy products. So, for example, the buttery taste of butter comes from butyric acid, and goat cheese derives its strong taste from a high level of caproic acid. Long-chain fatty acids like palmitic acids are components of phospholipids, which are the constituents of biological bilayer membranes. And so because these establish the borders of what is inside a cell and what is outside, without these long-chain saturated carboxylic acids, life could not exist. So now let's go over a few properties of carboxylic acids. So here we've got acetic acid, and as we can imagine, a carboxylic acid is an acid, as the name suggests, but they're pretty weakly acidic. So acetic acid is got a pK of around 4.8, so this will largely dissociate in water, but it's still not especially acidic. However, we can enhance the acidity by adding electron withdrawing groups on really any position, but especially alpha to the carbonyl. So here's trifluoroacetic acid. So we've got 3 fluorines there, and this has got a pK of 0.25. So that's already several orders of magnitude more acidic than acetic acid. And of course, we understand why, right? We know that the acidity of a molecule is proportional to the stability of its conjugate base. And so if we lose that proton, we've got that negative charge. And anything that's going to stabilize that negative charge will stabilize the conjugate base and therefore increase the acidity of a molecule. So we've got fluorines that are withdrawing electron density away, that are stabilizing that anion. And so that's why these increase the acidity of the molecule. And so we can see, we don't always see this, we can see longer chain carboxylic acids, and we can see halogens or other withdrawing groups in different positions. And I do have a practice problem that compares the acidity of various carboxylic acids, so that may be of use to you. But now that we've talked about some of the basic properties of carboxylic acids, let's go ahead and check out some applications. So let's look at some things that we can do with carboxylic acids. So obviously there's the potential for chemistry at the carbonyl carbon, but oftentimes we need to activate that first. So one thing we can do is react carboxylic acid with thionyl chloride. And so what's going to happen is first we're going to evolve HCl, and we're going to get to this intermediate here. and then we're going to evolve SO2, and we're going to get to the acid chloride. So an acid chloride is a more activated compound. These are great. From acid chlorides, we can do a lot of different things. So with an acid chloride, one thing we can do, this is a lot more susceptible to nucleophilic attack. So we can have an alcohol attack. So let's have that go ahead and attack here. And that is going to take us from this sp2 center to an sp3 hybridized intermediate. So now we're in sp3. And so we've got this Zwitter ionic intermediate here. We've got O- and O+. And some base is going to go ahead and grab this proton. Now, this could be some amine that's acting as a proton sponge is most likely the case, or something in solvent. But so a base is going to grab that, and we get to this situation here. And then this is going to go ahead and reform the carbonyl. But now we'll kick off chlorine. And so what we've done is we've generated an ester. So we've seen how we can go from a carboxylic acid to an acid chloride to an ester. So this is a useful technique for synthesizing esters. Now we do have to be aware that esters are susceptible to hydrolysis, especially in basic conditions. So we have to be careful. This can definitely hydrolyze and go right back to the carboxylic acid, which is a technique that we could do deliberately as well. And so that's a little bit of chemistry involving carboxylic acids to acid chloride to ester. We can also do chemistry with anhydrides. And so we may have an anhydride. Now this could be a symmetrical anhydride. If this was R, just a regular R, implying that the alkyl groups were identical, that would be a symmetrical anhydride. We can also have an asymmetrical anhydride. So that's with R prime where we have different groups here. Now that means that a nucleophile is going to be able to attack either carbon. So we could attack here, but we also could attack here. So either way, we're going to pop that pi bond up onto an oxygen, and when it comes back down, we're going to kick off the rest of the molecule, right? That's a very stable leaving group because of the resonance up the rest of the molecule there. So that's why this is much more receptive to nucleophilic attack than a carboxylic acid, right? A OH minus, right? That's not going to be that good of a leaving group, of course, but this whole portion of the molecule is because of that resonance stabilization. So with an anhydride, a nucleophile can attack one of these carbons. So we pop that pi bond up, comes back down, kicks that off, or it can do that here, pop this up, and when it comes back down, kick all this off. So we have two possibilities here. We can have the nucleophile on this carbon over here with this carboxylate, or we can have the opposite situation, right? If the nucleophile attacked here instead, then we would get this product and this carboxylate. So anhydride chemistry is very common. We can actually use very clever approaches where electronics, something about the electronics of the substrate will direct the nucleophile to one carbonyl over the other. So we have different ways of utilizing this in synthetic chemistry to get a desired product, one over the other. And then we also want to be aware of how we can possibly get amides. And so one example is this schotten-baumann amide. And so this is actually a very old reaction. It was discovered by these guys that we could take an acid chloride, and then if we add an amine in some organic solvent, and then we're running this in aqueous sodium hydroxide, we will go from here all the way to the amide. And so this is some old chemistry and pretty important chemistry, as amides are a very important molecule. So that's called the schotten-baumann amidation. So let's look at one more thing. Let's say that we want to synthesize some ketones from some carboxylic acid derivative. So say we want to go from an ester or an acid chloride to a ketone. Now, we may not be immediately sure of how to do this. Remember that we've talked a lot about Grignard reactions, but we know that starting with an ester, if we use some Grignard reagent, we're not going to be able to stop at the ketone, right? We know that one equivalent is going to add, it's going to kick off the alkoxy group, but then another equivalent is going to go ahead and attack, and we'll get two equivalents of that alkyl group on there. So that's not really going to work, but we have some other ways to do this. We have some other ways to get ketones, and so One way involves using something called a Weinreb amide. So this is a Weinreb amide. Notice that it is an amide, and we do have this methoxy group right here. We have N attached to OCH3. And so what we can do is we can actually use a Grignard reagent with this. And so the Grignard reagent is going to attack at the carbonyl carbon as we would expect. And then look at this adduct that we get as an intermediate. This is actually quite stable because we have this chelation going on. We have MgCl interacting with both of these oxygen atoms. And so now what's going to happen is once we hydrolyze this, we're going to get to this situation here. And when we protonate this, so this nitrogen can actually protonate, and that is going to cause an unstable situation where this is actually going to snap shut. So this proton can go, and we're going to snap that shut, and we can kick off the rest of this group here. And so that's going to give us our ketone. So we got that alkyl group on there from the Grignard reagent, and then this was stable because of this chelation. But then once that nitrogen was sufficiently protonated, this all just snapped shut, and that went away. So that's what got us our ketone. So there's one way that we're going to get a ketone from an amide. And here's another way, actually. We can do this another way, too. Let's say that we've got an amide here. We can react this with thionyl chloride. So let's just let's put this here, and this will go and attack sulfur. And so that's going to get us to this situation. So notice that oxygen attacked sulfur, and then that kicked off a chlorine, and that chlorine grabbed one of those extra hydrogens. So we've got HCl evolving as a byproduct. And now this is an interesting situation. What if we do this? So let's have this lone pair attack here. That is going to sever this carbon-oxygen bond, which is going to go right there. And then let's have this chloride grab that proton. So, and then I suppose that would probably go right there. So this is an interesting shuffling of electrons. That's going to get us to a nitrile, right? Because this nitrogen put the lone pair there, forming that third bond. We've now got a triple bond between the carbon and nitrogen. We've lost that carbon-oxygen bond. That went over here and attacked sulfur. So we're evolving SO2, and we're also evolving HCl. So we've got these byproducts, but we get a nitrile. So recall that a nitrile is CN, any CN triple bond. So this is a nitrile functional group. And now we can do Grignard again. So a Grignard reagent actually can attack the carbon on a nitrile just like it would attack a carbonyl. It actually behaves very similarly. And so that's going to pop this up there. And we've got N- interacting with the MgCl in the intermediate. So that behaved very similarly to other examples of Grignards that we would have seen. And then hydrolysis is going to take this all the way to the ketone. And so there is another way that we have to synthesize ketones from amides. So hopefully now we've gone through a lot of different derivatives of carboxylic acids and some of their synthetic applications. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.